I welcome you all to the India's most comprehensive preparation platform for GATE and ESCA BYJU'S exam prep. We are back again on the GATE Anchor series, and I am sorry for yesterday. Good evening, Sachin. I am sorry for yesterday. Yesterday, I was not able to take the session for Entropy because I was not very well. So, we are going to continue our session. We are going to cover some questions from Entropy. Also, we are going to cover the rest of the questions from availability and pure substances. Okay. So whatever we need to cover in 2 days, we are going to cover today. And today's session will be a little lengthy. Okay. We will not be able to finish today at 7. It will go a little longer, maybe till 7:30 because I want to cover everything today. Okay. So let's start with the brief introduction. So as you all know, if you are with me for last these days, so I have a teaching experience of around 4 plus years. I have MTech from IIT Kharagpur. I have done my MSc from Polytechnico di Milano. I have around 1.5 years of industry experience, 2 years of research experience, and some research publication. And my area of expertise is thermal engineering, basically. Okay. So Satin, I guess you were asking about my Telegram channel. So you can join me on this channel that you can see below. Okay. And other people who are joining this session today, they can also join this Telegram channel. I will be handling this channel and I will be uploading the PPTs here. I will be taking your doubts here. Okay. And whatever you want to ask, you can ask here. So I will be connected with you through this channel. Right. So I have asked these people to give me this channel, okay, as fast as possible. And thank you to them. Anyway, let's continue with today's session. So, Bhavya, I think we had a problem with this question, right? If you remember, it's been like 2 days, but anyway, we should not leave any doubts behind. So, there was one issue with this question. I mean, I don't think that was the issue, but anyway, first of all, this was in kilowatts, okay? Anyway, that was not our problem. The problem was you tried. So basically, we needed to calculate power required. So what we did, use steady flow equation, right? My audio is not very good today. I am having some cold, so please bear with me. Okay. Anyway, so it was m dot h1 plus v1 square by 2 plus q dot in is equals to m dot h2 plus v2 square by 2 plus w dot out. Okay. Now, uh, you all tried it. Okay, but the question was we converted h2. So what did we do? W dot out is equals to m dot h1 minus h2 plus v1 square minus v2 square by 2 plus q dot n. Okay. Now what we did, we converted h as u plus pv, right? This is what we did. And the question was, why did not we use h is equals to cpt? Okay. So to answer your question, you can use anything. Nothing is wrong. Both are completely correct. Because if you simplify it, it is what? cvt and pv is what? rt, right? So what is this? cv plus r T is equals to CPT. Okay. So ultimately, you will get the same thing. But then the problem is, why did not you get the same answer? Why did not you get the same answer? Okay. So the explanation behind it is that Q is in kilowatt, right? Yes, that is in kilowatt. Okay. But I don't think that was the question that time. It was a typing mistake. Okay. So the question was, why did not you get the answer by using CPT? Okay. Now, what usually happens is when we talk about, for example, we are taking working fluid as air, right? And what do we say? That Cp is 1.005 kilojoule per kg Kelvin. CV is 0.718 and R is 0.287. Okay, this is what we say. But basically, these values are nominal values. These values are defined at a particular temperature. Okay, at a particular pressure. Okay, so temperature is 300 Kelvin, pressure is 1 bar. So this is where how we define these values, and we say that it is taken as average temperature and pressure. Average temperature and pressure. Now what happens is that Cp is not always this. Cp is a function of temperature. Cp, Cv, whatever, they are function of temperature, and Cp is defined as, for example, A plus Bt plus Ct square plus something. So basically the value of Cp changes with temperature. Okay, the value of Cp changes with temperature. So these are not fixed values of Cp, but for simplification, most of the time, 99.99% of the time, we assume these values. Okay, no, that is what I am saying. Look, why did we use C plus PV? That is the question, right? Why did we use this formula? Okay, so because in the question specifically they have given U and specific volume, which we don't usually see. Okay, so they wanted us to use U plus PV. That is uh, first answer. Second is, then why did not you get the correct answer by using CPT? That is because this CP value is not 1.005 in this particular question. In this particular question. So if you go to internet and you see, or you refer a standard book and you see in the at the end of that book, you will see CP values, CP for water, CP of air. Okay. No, that is okay. That I mean that was one of the reasons that you got the wrong answer. But okay, but even if you use CP, okay, even if you use this, then also you will not get the right answer, I think. Okay, so you try with that, but that is also one thing. Okay, so that is one explanation that you cannot get the right answer by using only 1.005. Okay, so this is one explanation. But in this question, they give you U and they give you specific volume. So they wanted us to use U and U plus PV. Okay, that was one explanation behind it. Okay, now you try with both the things. You try with both the things. You take it kilowatt. You take it kilowatt and then try if you get the right answer, because the whole idea is to understand. So you try with that. Okay, let's move ahead. So this was the question I gave you. Could you please give me very quickly the answer so that we will move ahead? We have to do a lot of questions today. Sachin, please tell me, did you try this question? Yes, Bhavya, that is correct. All are correct. Sachin, did you try this? Sachin, are you there? So that we can very quickly move on to the next question. Okay, Sachin, I don't know if you can hear me, but I think, okay, Bhavya, I think that we are okay with this. Okay. So all options are correct. Okay, I gave Sir Clausius inequality. What is you want to ask what is Clausius inequality, or I mean, you first tell me, is did you try this question? Is it correct? What options are correct? So if you may have tried this, I don't know if I am getting delayed replies. But anyway, if you tried this, all are correct. Yes, Sachin, all are correct. Okay, so we can move ahead. We can move ahead. I hope whoever is there, they have tried it, and I think it's a very easy question. It's a very easy question, very simple question. Okay, Should not take more than I think 1 minute. Okay, very simple question. Anyway, so let's move on today's topic, which is entropy. We will move with availability and then pure substances. Three topics we have to cover today. Very quickly, we will move on. So, Sachin, you are asking Clausius inequality. I think you have some doubt in that. Okay. I think our first question is on Clausius inequality only. Okay. So, let's see this question and I'll tell you what is Clausius inequality as well. Okay. So, this question says there is an inventor that claims that he has developed a heat engine which absorbs 1200 kilojoule and 800 kilojoule from reservoirs at 800 Kelvin and 600 Kelvin respectively. And they reject 600 kilojoule and 1200 kilojoule as heat to reservoirs at 400 Kelvin and 300 Kelvin respectively. And this heat engine delivers 1200 kilojoule of work. Determine whether the heat engine is theoretically possible. Whether the heat engine is theoretically possible. So what do we have? We have a device, we have a heat engine that is absorbing heat from two reservoirs, not one reservoir. It is absorbing heat from 1200 Kelvin. How much? I'm sorry, from 800 Kelvin. How much heat? 1200 kilojoule. Then from 600 Kelvin, 800 kilojoule. Then it rejects heat. It rejects heat to two reservoirs. One is at 400 Kelvin and the other is at 300 Kelvin. How much is rejected? 600 kilojoule and 200 kilojoule. Okay. Now, it is also giving you work. It is also giving you work. How much work? 1200 kilojoule. So earlier what we see, how did we say that is it possible or not? By comparing it with reversible engine. So we can calculate what is the efficiency of a reversible engine. If its efficiency is more, then it means it's impossible. But it is interacting with more than one reservoir. Okay. So you see, it is T1 temperature, it is T2 temperature, it is T3, it is T4. So for these kind of problems, what do we have? In order to find out if this process, this cycle, this heat engine is possible, what do we do? We use Clausius inequality. Clausius inequality. What does Clausius inequality tells you? What does Clausius inequality tells you? It tells you that it tells you that cyclic integral of dq by t is always less than equal to 0. Cyclic integral. It is valid for a cycle. Okay. So now heat engine is a cycle, right? So cyclic integral of dq by t is always less than 0. It is equals to 0 for a reversible cycle. It is less than 0 for an irreversible cycle. Sachin, does that answer your question? Do you understand what is Clausius inequality? Okay. If it is greater than 0, if you will get that cyclic integral of dq by t is greater than 0, that means that cycle or that device is impossible. Okay. So this is your Clausius inequality. Okay. So what do? We will see that Q1 by T1 plus Q2, whatever heat exchanges are interacting with the cycle, okay? T2 plus Q3 by T3 plus Q4 by T4. For this cycle to be possible, it should be less than equal to 0. It should be less than equal to 0. Now, can you very quickly answer this question, that is this cycle theoretically possible or not? Very quickly, can you calculate this? Let's say this is Q1. Let's say this is Q2. Let's say this is Q3 and this is Q4. Can you very quickly tell me, is this cycle possible or not? So it is Q1 is 1200. Very quickly calculate it and tell me. Plus Q2 is what? 800. Plus now Q3 is what? Q3 is heat rejected. It is going out. So it will be minus 600 by 400 plus minus 200 by 300. Cyclic integral is coming positive. Of course, it is coming positive. How much is it? How much is it coming? How much is it coming? What is the value? It's 2 by 3. It's, yeah, I think it's, yeah, that is correct. It is 2 by 3, which is 0.67. So is 0.67 less than equal to 0? No, it is greater than 0. So if it is greater than 0, that means this is not possible. This is not theoretically possible. This is impossible. Okay. I hope. Sachin, is it clear? Then we will move ahead. We will move ahead to the next question. Okay, so, and we will move ahead. Okay. Okay. Next question. 4 kg of water at 40 degrees Celsius is mixed with 6 kg of water at 100 degrees Celsius in a steady flow process. Calculate temperature. We have to calculate change in entropy and unavailable energy with respect to energy receiving water at 40 degrees Celsius. Okay, 3 things we need to calculate. Okay. Now I hope you already know what is unavailable energy. Okay. So for example, if I am supplying heat Q1, total heat that I am supplying to a heat engine is Q1. Okay. So from this Q1, some work is generated. This work is called as available energy. Okay. And what is rejected is unavailable energy. What you cannot utilize, what cannot be converted into work is called as unavailable energy. Okay. Now, what is happening? So 4 kg M1 is 4 kg of water at what temperature? 40 degrees Celsius. It is mixed with M2 is equals to 6 kg. Okay. And what is the temperature? T2 is equals to 100 degrees. And they are mixed in a steady flow process. So here we have M3 and temperature will be T3. Okay. Now, first we need to calculate temperature of the resulting mixture. Okay. So can you calculate M3? What is M3? It is a steady flow process. Steady flow process. Steady flow process. Okay. So you can use steady flow equation as well as you can use continuity equation. Continuity equation is what? Mass conservation equation. Mass conservation equation. So mass in is equals to mass out. What is mass in? M1 plus M2. What is mass out? M3. Okay. If I talk about this section, so M1 plus M2 is equals to M3. M1 is 4 plus 6 is equals to M3. M3 is equals to 10 kg. M3 we know. Now I need to calculate T3, temperature 3. So what will I do? I will use steady flow energy equation. Steady flow energy equation. Okay. So steady flow energy equation, what is it? Energy in is equals to energy out plus change in energy of the system. Now, because it is a steady flow system, this is zero. This is zero. Okay. So whatever in is equals to out. Okay. Now what is in? In is M1 H1 plus M2 H2 is equals to M3 H3. Okay. Now what we have done? We have neglected kinetic and potential energy change. So only enthalpy is there. Okay. That is correct, Bhavya. That is absolutely correct, I think. Yeah. 349 Kelvin. Absolutely correct. Okay. So Sachin, have you also solved it? Tell me very quickly. So I'll go a little quick on this. Okay. M1 is 4 into Cp into T1 plus 6 into Cp into T2 is equals to 10 into Cp into T3. Sachin, have you also calculated this? Very simple. Nothing is there. Cp of water is 4.18 I'm sorry, kilojoule per kg. Okay. But anyway, we don't need it. We can directly cancel it here. Okay. T1, you know, T1 is 40 degree. T2 is 100 degree. Okay, so 40 is what? 313 plus 6 into 100 is what? 373. 10 into T3. Sachin, okay, I hope you got the answer. It is 349 Kelvin. Very nice. Very nice. Okay. Then the next part of this is change in entropy. So do you have any idea how we will calculate change in entropy? So you see, if you have been doing entropy with me, if you have followed my lectures, you would know that always change in entropy I can calculate by dq by t. Okay, dq by t. So I have to integrate this. Now I can say S2 minus S1 is equals to dq by t. Now if it is an isothermal process, if the temperature is not changing, if there is an isothermal process, then I can directly write S2 minus S1 is equals to q by t. Do I need to integrate it? I don't think so. Okay, I don't need to, because I'll take 1 by t out, dq 1 to 2, and it will be q2 minus q1. So earlier there was no q, so it is only q2 by t or q by t. Okay, so in case of isothermal process, you can directly calculate like this, q by t. But if if temperature is changing in the process, if temperature is changing, non-isothermal process. For example, right now my temperature is changing. How? It is going for water 1, it is going from 313 Kelvin to 349 Kelvin, isn't it? For my water stream 2, it is going from 373 Kelvin to 349 Kelvin. So what is changing? Temperature is changing. It is a non-isothermal process, right? Now you can't take temperature out. You have to dq by t. Now this is how you have to do it. So dq is what? dq I can say either du plus pdv or dq is equals to dh minus vdp. Okay. Now there are two conditions here. If I am using for liquids and solids, or I am using for gas. Now for liquids and solids, what happens? Look, their volume you cannot change. Their dv is equals to 0. Okay. First condition. Second is Cp is equals to Cv is equals to C. Two conditions are there. Okay. So if you put this here, so you see dV is 0 for liquids and solids. So only you can write here is du by t. Okay. So du by t is what? mc dt by t. So I can write mc ln t2 by t1 or t final minus t initial. I hope it is clear with. I hope this is clear. Okay. Now this case is only for solids and liquid. For gases, dV is not equal to 0. So there will be a S2 minus S1 is equals to mCV ln T2 minus T1 plus R ln V2 by V1, or because there these terms are not 0, so there will also be these terms for gases, okay. mCp ln T2 by T1 minus P ln R ln P2 by P1. Okay, so for gases you have to use these formula. If it is a gas, for example, water vapor is there, air is there, so you have to use this. For liquid, for water, for example, in a particular question, what is there? So I can use this. Okay. Very quickly, because I don't have space, let me very quickly remove this. This was just for a quick revision because I have already taught this. So next time I will not tell you this. Okay. So now I need to calculate entropy change. So what will I do? Entropy change total is equals to entropy change of water 1 plus entropy change of water 2. Okay. Very quickly calculate this. Now you know how to calculate this. Okay. Mass of water 1, C of water, which will remain constant, ln T final by T initial. This is for water 1, stream 1, plus mass of water 2, C ln T final by T initial for stream 2. Now you calculate this very quickly. Tell me what is it? Total entropy. M1 is 4 kg. This is 4.18 kilojoule per kg Kelvin into ln. T final is 349, but T initial was 313. Okay. Plus this is 6 into 4.18 into ln 349 by 373. What will you get? You will get in kilojoule per Kelvin. You will get in kilojoule per Kelvin. Kilojoule, right? Not joule, right? How much did you get? 152. One second. That doesn't seem correct to me. Can okay, 152.37. I think that is correct. Little bit here and there. Okay, just calculate it because I have written I think 160 or something. But anyway, I think that is almost correct. Sachin, are you getting this? Avya, how much did you get in kilojoule? Zero 0.51. Okay, anyway, I think that is correct because I have 0.16. Anyway, no problem. That is correct. Okay. So let me, I am not calculating this. I am assuming you have calculated it correctly, and you will get 0.1523 kilojoule per Kelvin, or 152.3 joule per Kelvin. Sachin, yes, that is correct. Always try to put units, okay? Yeah, that is correct. Okay. So joule per Kelvin. That is the change in entropy. Change in entropy. Now the next is unavailable energy. Unavailable energy you need to calculate. How will you calculate unavailable energy? So basically what happens, you see, the water that entered into the pipe at 40 degrees Celsius, for example, you can show by this on a TS diagram, okay? Now this will have some energy. This will have some energy, but then it is mixed with water at 100 degrees Celsius. So its temperature increased to what? T3, T final, which is, let's say this is 313, right? 349 Kelvin, okay? 349 Kelvin. Now, if you see here, look, out of this, if it has some energy, okay, there is water which is at 349 Kelvin. So it has some energy. Now, this is your available work. This is your available energy, which you can utilize to convert into work. This much energy can be converted to work. But if you fix your lower temperature, that means if you are running a heat engine and you are rejecting heat at 40 degrees Celsius by using that water, okay? So if you are rejecting heat at 40 degrees Celsius, then you cannot go below 40 degree. You cannot go below this. And this much energy will be lost. This much energy will be lost if your lower temperature is 40 degrees Celsius. Okay? If your lower temperature is, so this is your unavailable energy. This is your unavailable energy. So how can you calculate unavailable energy? Unavailable energy is equals to T1, which is 313 Kelvin, into change in entropy for water 1. Okay, for water 1. So T1 we know it is 313 Kelvin into MC ln T final by T initial of 1, of first water stream. Okay. Now can you very quickly calculate this and tell me? 4 So whatever you get, you will get in kilojoule. Okay, very quickly tell you how much is it. 569. That is absolutely correct. 569. 569.75 kilojoule. Sachin, is this okay? Where are other people? Why are you not replying to the chat? I think there are more than 2 or 3 people who are watching. Please reply. Otherwise, I mean, you also be a part of this, okay? Okay. Okay, then let's very quickly move on. Okay. Now, water of mass 10 gram. Water of mass 10 gram at 25 degrees Celsius is converted into steam at 300 degrees Celsius at 1 bar atmospheric pressure. The specific heat of water is given constant. Water is constant. Specific heat of water. Latent heat of vaporization is given. Consider water vapor follows ideal gas equation having R is this and Cp is a function of temperature. It is the same thing that I was telling you. Okay, Cp is changing with temperature. So constants are given. Okay, I'll tell you one thing. This is what I gave you. I wrote you there. I wrote it there. But not always CP depends on temperature according to this equation. Okay, it could be any other equation as well. Now, so what is happening? Let's try to visualize this. You see, some water is there. How much mass of water is equals to 0.01 kg? Okay, and temperature is 25 degrees Celsius, and it is converted to steam. Now it is converted to steam, and the steam temperature is 300 degrees Celsius. That is the final temperature of steam. Pressure remains constant. Pressure remains constant as 1 bar. So I need to calculate entropy change. Now we all know how to draw this on a TS diagram. So basically you will be giving some heat here. Okay. So if I draw a TS diagram like this, at constant pressure, 1 bar, this phase transfer phase change will take place. Okay. So water is there. Let's say water is here at T1 is equals to 25 means 298 Kelvin. Okay. Now its temperature will increase to the saturation temperature of 100 degrees Celsius. This is T saturation, which is 100 degree Celsius. So 373 Kelvin. Okay. Now you will still give heat. Okay. So but the temperature will remain same. It will convert from saturated liquid to saturated vapor. And then further it will convert into vapor at T final, or let's say T3 T saturation, and this is T final is equals to 300. So 300 is how much? 573 Kelvin. Okay. So this is what is happening. Now they are asking calculate entropy change for vaporization. What is entropy change for vaporization? You need to calculate how much change of entropy is happening during this period. Okay. So you need to calculate. This is entropy change during vaporization. Second is entropy change of vapor during vapor. So this is your entropy change during vapor. This is your entropy change during vapor. Okay, from here to here. Temperature is changing, right? Here temperature is constant. Then they are asking entropy change of water. So you have to calculate how much entropy is changing here. Also temperature is changing. And they are asking total entropy change of the system. So you have to calculate all of them. You have to add all of them. So I think now it's fairly simple for you, isn't it? I just showed you how to calculate entropy change for solids and liquid. So first is water. You can calculate, temperature is changing from what? 298 to 373 Kelvin. Then I also told you how to calculate entropy change at constant temperature. Q by T. You know Q. Okay. That also you can calculate. Then you know how to calculate entropy change when gas is there. Okay. So it's very simple now. I hope it's very simple. Now entropy change for vaporization. So entropy change of vaporization is basically what? Look. Again, I'll tell you one more time. ds is equals to dq by t. Okay. Now, if I talk about vaporization, what is happening? My temperature is constant at saturation temperature. So I can take my temperature out and I can integrate dq. So I showed you it is q by t. It is q by t. Okay. Now what is q? How much heat transfer is taking place here? The heat transfer that takes place to convert saturated liquid to saturated vapor is called as latent heat of vaporization. So this heat you are giving, very right, Bhavya, that is correct. So it is mass into latent heat by saturation temperature. Mass you know, latent heat you know, this is mass, this is latent heat. Saturation temperature is 373. So very quickly tell me how much is DS vaporization? 60.59. That is correct. That is absolutely correct. Joule per Kelvin. Okay. So that means this option is correct. Okay. So mass is 0.01 kg into 2260 kilojoule per kg upon T saturation is 373. Okay. So I hope you calculated it correct. Yes. Okay. 60.58 joule per Kelvin. Okay. You will get in kilojoule, but you have to convert. You have to divide by 1000. Okay. I'm sorry, you have to multiply by 1000. Okay. So, Sachin, are you able to get this? Then we will move ahead. Sachin, 60.58, that is correct, joule per Kelvin. Okay. Now, very quickly, let's move on to entropy change for vapor. So, vapor is what? It is a gas. Okay. And I told you how to calculate for gas. So, you have to use what you have to use. S2 minus S1 is equals to M Cp ln T2 by, let's say, T final by T initial minus R ln T mRNN. Right? This is how you can do it. I told you earlier. Okay. Okay, I removed that. Anyway, so for gases you have to calculate like this, because there dV was 0, but here it's not. So either you have to calculate in terms of volume or pressure. Now when this is happening, you see pressure is constant. Pressure remains at 1 bar. Pressure is not changing. All this process is happening at T is equals to 1 bar, isn't it? All this process is happening at 1 bar. So that means pressure remains constant in this particular process, not every time. In this particular process, pressure is constant. When pressure is constant, this will go away. This will, okay. So this will go away. Okay. So now what do you have? You have M Cp ln T final by T initial. Now what is T final? T final for vapor. Okay, vapor is changing from, this is for vapor. So T final is 573 and T initial is 373. So for vapor, the temperature is changing from 373 to 573. Okay, so calculate this. Now the problem that is coming here, okay, there is one issue here. Okay, there is one issue that Cp is not constant. Cp is not constant. So we cannot directly use this. We cannot directly use it. How will we do this? So you see, let me tell you one more time. Let's start with the basics. Let's start with the basics. What are the basics? ds is equals to dq by t. Okay, ds is equals to dq by t. Now can I write dq is equals to dh minus pdv minus vdp by t? Okay, and can I write dh by t minus vdp by t? I can do this, right? Now I told you already pressure is constant, so change in pressure will be zero. Change in pressure will be zero. So this part will go to zero. So this you can remove. So now what do we have? We have mcp dt by t. mcp dt by t. Now the formula I wrote earlier, it was in the case of constant cp. It was in the case of constant cp. Here cp is not constant. Cp is what? Cp is equals to a plus bt plus ct square by r. This is your cp. So cp depends on temperature. Cp depends on temperature, so you cannot take cp out. You cannot take directly cp out, okay? But you can take what? S2 minus S1. You can take mass out. You can take this R out, okay? But A plus BT plus CT square, this will remain inside the integral because it is a function of temperature into dt by t, into dt by t. So I can also write mr A by t plus B plus CT dt. Okay, is it clear with you? I mean, are you able to understand this? Okay, just to give you an idea, that's I mean, usually you don't get this kind of questions, but you can get. There is no rule that you cannot get this kind of questions. Usually they give you cp as constant, okay, but you need to get some idea about these kind of questions as well. Okay, could you very quickly tell me, is this okay, or should I need to explain it more? The earlier formula that I gave you, it is in the case of when cp is constant, so cp is taken at average value. Now let's move on. So if you integrate this with respect to dt, what will you get? mr a. Please do not ask me to do the integration, okay? I'll directly give you the values, okay? So it will be from t1 to t2 or t final to t initial. Okay, ln t final minus t by t initial plus b t final minus t initial plus c t final square minus t initial square, and this is your S2 minus S1. Okay, you have integrated this. When you have integrated this, you have got this. Now you know everything. You know m. M is 0.01 kg. R is 0.462 kilojoule per kg Kelvin. You know A, you know B, you know C, you know T initial. T initial for vapor is what? 373 Kelvin. T final is what? 300. So this is 573 Kelvin. So you can put this and calculate. T final is temperature that we have. Is there a issue? Is there a issue, Bhavya? Sachin, what is the issue? T final will be for, we are talking about vapor, okay? We are talking about for this vapor, T initial is this. and T final is this. Vapor temperature. Video lecture. Is it running now, Sachin? Is it okay now? 8.37. Let me check. Okay, Hardik. Thank you. Okay. Okay, anyway. So, by the way, that is correct. This is 8 point for vapor. It is 8.37 you calculated. That is correct. Okay, I got 4.3, but it's okay. Okay, so okay, so this is for vapor. Now we have to calculate for water. Very quickly, you can calculate this without me even writing the formula, because we have already done this. Now water temperature is changing from T1 25 degrees Celsius. T initial for water is 25, okay, is 298 Kelvin, and T final is basically T saturation is equals to 100 degrees Celsius or 373 Kelvin. So we know how to calculate this. Entropy change for water is what? We just did it. Very quickly tell me how much is it? Do I need to write the formula? 9.518. That is absolutely correct. 9.518. That is absolutely correct. Sachin, are you there? Is it? Are you able to reconnect it again? M of water, Cp of water, ln T saturation, which is T final, upon T1, which is T initial. Just put the values. Okay. Cp of water is given, and mass of water we know. Everything is fine here. Okay. So it is 9.518 joule per Kelvin. So now tell me what is the total system, total entropy change for system. Total entropy change for system is equals to entropy change for water plus entropy change during vaporization ठीक ही है. So very quickly tell me how much is the total entropy change of system. Very quickly tell me how much was water. Water is 9 point how much? 9.518 during vaporization. This is 60, right? This is 60.59 you calculated. And during this is 8.37. So 78. I hope that's correct. That must be correct. I have not the right answer here, but I think that is correct. Okay. So that doesn't seem to be the entropy change of system. Okay, that doesn't seem to be the entropy change of system. Rest of them I think are correct. Okay, this is 9 point. This is also correct, and this is also correct. Okay, so now let's very quickly move on to the next question for today. Okay, now a furnace can supply heat steadily at 1500 Kelvin at the rate of 500 kilowatt. The maximum amount of power that can be produced by using the heat supplied by the furnace in an environment at 300 Kelvin. Okay, so what is happening? We have a furnace and it is supplying heat. Furnace is at constant temperature of, so let's say we have a furnace here that is at high temperature of 1500 Kelvin. Now it can supply heat at 500 kilowatt Q1. Okay. Now I need to calculate maximum amount of power that can be produced from this furnace. So in order to produce power, I need to install a heat engine. So now heat engine will supply some, will reject some heat as well. At what temperature? 300 Kelvin. Reject some heat. Okay. Now I need to calculate maximum work. Maximum work. How much maximum work can I calculate? 400. That is absolutely correct. Very nice. Very quick. Very nice. Okay. So other people are here. Let me very quickly solve this. Okay. So you see efficiency of a heat engine is given as 1 minus Q lower upon or Q rejected upon Q absorbed, or also is equals to work upon Q supplied. Okay. But in question they are asking maximum amount of power. Maximum amount. Maximum you will get for reversible. For reversible only. Now for reversible you can also write T2 by T1 and then you can write maximum work on Q supplied. Now you can calculate this. 300 by 1500 is equals to maximum work I need to calculate. Q supplied is 500. Okay. Now this is what? This is 1 by 5, 1 by 5, right? So when you calculate this, maximum work is 400. Okay, this will be 0.8 is equals to work maximum by 500. So you will get 400 kilowatt. Okay, very nice. 400 kilowatt. So let's move ahead then very quickly. Okay, now 800 watts of heat is steadily lost through a plane wall. Okay, what is happening? We have a wall. Now steadily, you know, at a constant rate, 800 watt of heat is lost. Why? Because one side is maintained at 25 degrees Celsius. This side, one side is maintained at 25 degrees Celsius and the other side is maintained at 2 degrees Celsius. Ambient, T ambient is 0 degrees Celsius. The rate of irreversibility within the wall. Irreversibility within the wall we have to tell. Within the wall, how much is the irreversibility? Now you all know that by Gauss-Stoller theorem, irreversibility can be given as T naught into entropy generation. Entropy generation. Okay. Now, how do you calculate entropy generation? T naught, we know T naught is the temperature of surrounding, which is 0 degrees Celsius, which is 0 degrees Celsius. Okay. Now, how will you calculate entropy generation? Entropy generation. So, entropy generation, how can you calculate? Entropy generation. You see, entropy is changed because of two ways. There are two ways entropy can change. First is entropy transfer. Second is entropy generated inside the system. Now you see, when this heat is getting transferred, when the heat is getting transferred here, okay, this heat is getting transferred here. So there will be some entropy transfer because of this heat transfer. Also because of this heat transfer, there will be a entropy transfer. Now the difference of that will give you entropy generated inside the body, inside the wall, inside the body. Whatever system you are assuming, it will give you entropy generation. Okay, so entropy generation will be equal to Q upon T. Okay, summation of Q upon T. So here what we have, Q1, let's say this is Q1. Okay, basically Q is same, but let's say this is T1 and this is T2. So Q, from one side where it is entering, so this side 25-degree heat transfer will happen from high temperature to low temperature. Okay, high temperature will lose heat and low temperature will absorb heat. Okay, so high temperature will minus Q upon T1 plus Q upon T2. Now very quickly tell me what is entropy generation here. Very quickly tell me what is entropy generation. How much is the entropy generation? Can you very quickly tell me how much is the entropy generation? Q is same. Q will remain same. Only the same heat is flowing. Okay. It is 0.2245. Very nice. 0.2245. So this much. And you also know, look, if you get this negative, that means you have done something wrong. Entropy generation is always greater than equal to 0. Always greater than equal to 0. If, for example, you take negative sign on the other side, okay, if you take positive here and negative here, then you will get a negative value. That means you have done something wrong. Okay, always cross check your answers. There are few things that you should know. There are few things that change according to few rules and you should follow them. Okay, so entropy generation, irreversibility is T naught, which is 273 into entropy generation, and you have got 61.3. That is very correct. That is absolutely correct. Okay, so this is what? This is Q is in joule per, it is in watt per Kelvin. So this is what? Watts. Okay, very nice. Let's move ahead then. Let's move ahead. Okay, so this is irreversibilities. Last question. Consider a heat engine. Consider a heat engine. Now you have to solve it yourself. Which of the following statements are correct? Which of the following statements are correct? The reversible power. So this heat engine is given to you. First temperature is 1500. Heat supplied is 700 watts. Actual work that this engine is giving is 320. So how much is Q rejected here? How much is Q rejected? How much is Q rejected? 380. Now they are saying the reversible power. Reversible power means maximum power. Okay, reversible power means maximum power. A is correct. A must be correct. Yes, that is true. How about the next one? So maximum or reversible is 1 minus 320 by 1500 equals to reversible work upon Q supplied. Okay, so I don't have the solutions for this, but I think that is correct. So A is correct. That is, I think that is correct. Rate of irreversibility. What do you mean by rate of irreversibility? So irreversibility is basically, you see what is happening. There is a reversible power, and due to irreversibility, look, there is a reversible engine. It will give you maximum work. Then because of irreversibility, your actual heat engine will give you your actual work. So there is some work lost. There is some work that is lost that could have been obtained, but it is lost because of irreversibility in the system. So that irreversibility is equals to lost work, or I can say maximum work minus actual work. Okay, very quickly tell me what is the rate of irreversibility. Is it correct or not? Second law efficiency. How can you calculate second law efficiency? Second law efficiency is actual work upon maximum work. Thermal efficiency, I think you have calculated. Thermal efficiency is equals to work actual upon Q supplied. Q supplied. Sagar, which one is correct? Are you saying all are correct, or which one is like? Yes, every option is correct. Every option is correct. Okay. So if we are on the same page, then let's move ahead. If we all are on the same page, then we can move ahead. I'm sorry, Sagar, I did not understand. What are you asking? Are you asking something? You are telling something? Please just use few more words and tell me. Okay, then we will move ahead. Okay, because it's already 7:09, and we will be together for, I think, more 25 minutes, 20-25 minutes. Okay, so let's move ahead. Sagar, please tell me if you want to ask something, if you want to say something, please tell me. I'll take it later on. Okay. Okay, let's move ahead then. Okay, very quickly. Now we have come to pure substances. Pure substances, okay, where you calculate what is dryness when phase change is happening, how to calculate dryness fraction, how to calculate enthalpy, entropy, and all these specific volume. Okay. Now, first question, very basic question. You should all be able to solve this without any help. Okay. Steam. We have steam having following properties at 8 megapascal and specific volume of 0.1674 meter cube per kg. Which of the following statements is and are correct? Okay. So tell me, dryness fraction of mixture of steam is 0.903. Okay. Very quickly tell me, is it correct or not? Which one is correct? So you see specific volume is given. First pressure is given 8 megapascal and specific volume is given 0.1674 meter cube per kg. Now, in order to identify if it is a mixture of liquid and vapor, what can we see? We can compare here. You see, our specific volume lies between these two values. Aman, thank you. Please solve the next question. We will move ahead very quickly, okay? So, in order to see that if it is saturated liquid, if it is saturated vapor, it is a mixture. So, what can you do? You can compare this value with these two values. So, you see it is coming in between. You see your specific volume is greater than Vf and it is less than Vg. That means that what does it mean? What does it mean? This is your TS diagram. Okay, so this value gives you Vf and this value gives you Vg. So if your value is somewhere in between, you see this value, this is 0.001040 and this is 0.198. So it directly tells you that it is liquid. You know dryness fraction will be between 0 and 1. Okay. Then you calculate. So when you calculate this, what will you get? So V is equals to Vf plus X Vg minus Vf. Vg minus Vf. Okay. Vg minus Vf. You know everything. You know this V 0.1674. Vf is this value 0.001040 plus X we need to calculate 0.198 minus Vf 0.001040. X you can calculate. Bhavya has calculated. How much is this? Okay, I don't have the solution for it, but that is correct. That is correct. It is this option. Okay. Aman, are you also solving it? Have you gotten the answer? Sachin, we have lost today, I think. Anyway, enthalpy, the same thing you are going to do with enthalpy. Okay. Now you know H. Now you know X already. X you have calculated 0.845. Very nice. Okay. Now X you know. H you can calculate by HF plus X Hg minus HF. So HF you know, Hg you know, X you know. You can calculate enthalpy at this particular point. So this was just to 2455. Okay, probably that is correct. It should come maybe like this. I don't know. I have not calculated this. But as much as I remember, C and D was the right answer. So maybe this option is written wrong. I am not very sure about it. But I think that you should know the method. Okay? The objective is idea is to know how to calculate it. Typing mistakes can always happen. That is not a problem. Okay. So anyway, so what are we doing? Okay, so that is correct. Okay. 2488. I hope that, yeah. So this is correct. Okay. I have not solved it, so I cannot be very sure. Anyway, so this comes to be 2488 kilojoule per kg. Okay. So that was a very basic question. I don't think we learned anything new with this, right? We already knew all this. Let's move on to the next question. Okay. Saturated water vapor enters an adiabatic turbine at 0.8 megapascal. So we have a turbine. We have a turbine. Enters here, comes out here. Here pressure is equals to 0.8 megapascal. Okay. So this are the properties here. These are the properties here. And exit pressure should be, of course, it will be less. Turbine is there. P2 is 0.1 megapascal. Okay. So you have to follow this line. If you talk about exit, if you are, so this is your inlet, this is your exit. Mass flow rate of water vapor is 25 kg per second. 25 kg per second. So mass also I know. So can I draw this on a TS diagram? Yes. I can draw this on a TS diagram. TS. Now, we are working, this turbine is working between two pressures. Okay. The first pressure is higher pressure. Second pressure is lower pressure. So this is 0.8 megapascal. This is 0.1 megapascal. Now they are saying saturated water vapor. Saturated means you are at this point. You are at this point. Saturated. These points are very, very important. Saturated means you are at this point. Okay. Now expansion will happen and you will come at this pressure. Expansion will happen. You will come at this pressure. Okay. Now they are asking, what are they asking? They are asking quality of steam at the exit of the turbine after an isentropy expansion. So isentropy expansion means entropy will remain same. So you will come like this. Entropy will remain same. S1 is equals to S2. S1 is equals to S2. Entropy will remain same. Quality I need to tell you. Now tell me what is S1? What is S1? S1 is equals to S2. What is S1? Can you tell me what is S1? S1 is the entropy of at 0.8 megapascal and saturated vapor. Saturated vapor. Okay. So how much is S1? How much is S1? S1 is 6.6628. It is 6.6628. Now S2, you know, S2 is this point. So you cannot calculate S2 directly. What you will have to do? You will have to calculate S2 is equals to SF, which is this value, plus X S right. So you will put it here, SF plus X Sg minus HF. Now you have, when talk about S2, then you have to talk about this pressure, lower pressure. So SF is this, Sg is this, and you can calculate X. Bhavya has calculated, let me check, that is correct, that is absolutely correct, 0.88. Are you, other people are also solving it? Could you please confirm it? Is it correct? Are you also getting the same answer? Look, people who are there, who are watching and not answering, it's my humble suggestion that please be a part of the class so that you will get the confidence of what you are solving is correct. Okay, I really appreciate people who have the confidence that they can, like, if you, even if it is wrong, it does not matter, but by solving it you gain the confidence that you can solve it. Okay, so please try to be one step ahead in the class. If it is wrong, answer is wrong, it does not matter. We are not giving the exam here. The idea is to learn. Okay, so anyway, SF, you know, SF is this, SG is this, and you have calculated this, it is 0.88. That is absolutely correct, and this is X2. Okay, that is X2. Now next is, they are asking, if the steam enters the turbine at saturated vapor, the power produced by the turbine. Power produced by turbine. So how do you calculate power produced? It is a turbine. It is a steady flow process. It is a steady flow process. So what is happening in steady flow energy equation? Steady flow energy equation. So it is entering at M in H1. Now I neglect kinetic energy and potential energy. So I am not going to write that. Plus Q in, okay, Q in, okay, is equals to M dot out H2 plus work dot out. Okay. Now Q in will be 0 because no heat transfer is happening. Adiabatic expansion was happening. Okay, isentropic, which is reversible adiabatic. Okay. So work output I can calculate M dot H1 minus H2, isn't it? M dot H1, M dot is given. M dot is 25 kg per second, if I remember right. Okay, let me check one more time. 25 kg per second, that is correct. Okay, H1. H1 is how much? H1 is 0.8 megapascal and saturated vapor Hg at 0.8 megapascal, which is 2769.10 kilojoule per kg. Okay, how will you calculate H2? How will you calculate H2? H2 you can calculate by H2 you can calculate at 0.1 megapascal HF plus X Hg minus Hf. Now X you have already calculated. X you have already calculated. Okay. Hf is this. Hg is this. Very simple. Okay. So H2 you can calculate. You put the values, you give me the answer. H2, how much is H2? How much is H2? 9114.25. That is absolutely correct. And it will be in kilowatts, yes. So 25 kg per second. How much is H2? How much is H2? Can you tell me how much is H2? 2404. That is correct. Okay, and this is kilojoule per kg, and when you find it, it is 9114.25 kg, and kg will get cancelled. Kilojoule per second, which is kilowatt. Very nice. Okay, so let's move ahead. Okay, so I think this is the last question for today. Now, what do we have? We have a frictionless piston cylinder device, contains 0.02 kg of steam. Okay, so we have a piston cylinder device. Piston is here. Piston is here. Okay, and it has 0.02 kg of steam, and pressure is 0.6 megapascal. 0.02 kg of steam at pressure P1, 0.6 megapascal, and temperature is 200 degrees Celsius. Now what are we doing? We are doing expansion. Piston will move, volume will increase, piston will reach somewhere here. Final pressure P2, they are saying 0.12 megapascal. Total displaced volume, this is displaced volume, is equals to 0.0188 meter cube. Okay, and steam pressure and volume is related to 1.24 is equals to constant. And then they have given us properties. They have given us properties at 0.6 megapascal. Specific volume is given, specific enthalpy and internal energy is given, and then 0.12 megapascal we have these properties given. Okay, so what do we need to calculate? What do we need to calculate? Which of the following is and all are correct? Work done by the steam in the expansion process is 4.68 kilojoule. Dryness fraction we need to calculate, change in internal energy and magnitude of heat transfer. Okay, so look, rotary turbines and compressors are considered as open system. Reciprocating are basically they are intermediate operations, they are considered as closed systems. Okay, now they are saying pressure and volume are related like this. Now we all know how to calculate work done in a process in which it is a polytropic process, right? It is a polytropic process. So we know how to calculate work done in that particular process. It is a polytropic process. How do I calculate? P1 V1 minus P2 V2 upon N minus 1. N minus 1. So you all know what is P1? P1 is 0.6 megapascal. P1 is 0.6 megapascal. P2 is 0.12 megapascal. Okay. Now we need to calculate V1 and V2. Okay. V1 and V2. How do you calculate that? Work done 4.6 kilojoule. Let me check. That is absolutely correct. That is absolutely correct. How do you calculate that? How do you calculate that? 4.6, right? That is absolutely correct. Kilojoule. Okay. Then calculate dryness fraction and change in internal energy. Okay. So what are we doing? Look, this is a piston. And they are saying this volume is given to us. This volume is 0.0188 meter cube. Now V2 Yes, that is correct. Okay. V2 minus V1, we know how much is it? 0.0188 meter cube. Yes. Okay. Now you can calculate V1 and V2. Okay. You can calculate V1 and then you can calculate V2 by this. And then you can put it here. And already you know P1, P2 you know. And then you can move on. How much is V1? V1 is equals to V1 is equals to specific volume is given to you and mass is given to you. Okay. So V1 is equals to specific volume is equals to V1 by M. So V1 is equals to specific volume into M. Specific volume is 0.352. Okay. Into mass is 0.02. So you will calculate V1, which is 0.007. I think that is, yeah, meter cube. Now you have just seen what? That V2 minus V1 is equals to 0.0188. So you can calculate V2 also from here. How much is V2? V2 is, that is correct. V2 is 0.0258 meter cube. Okay. So now you know V1, you know V2. What else is left? Nothing else. You can calculate work done. Okay. You can calculate work done. And work done is 4.68 kilojoule. Now next is dryness fraction after expansion. Dryness fraction after expansion. Okay. So how do you calculate after expansion? You see, they are saying this is what? This is 0.6. One is 0.6 megapascal and the other is 0.12 megapascal. Okay. Now V2 you have calculated. V2 you have calculated to be 0.02584. Isn't it? Meter cube. Now can you calculate specific volume at this point? Yes. V2 by M. So 0.02584 and mass is 0.02 and this is 1.292. Okay. Now you see here specific volume. This specific volume is in between these 2 points, VG and VF. So your specific volume at point 2 is 1.292. Okay. And you can see that this V2 is greater than this VF, isn't it? And it is less than VG. It is less than VG. That means it is a mixture. It is a mixture. Okay. It is a mixture of liquid and gas. Okay. Now nothing is left then. You know V2, you know VF, you know VG, you can calculate X. Okay. Nothing is left. You know that V2 is equals to VF plus X, VG minus VF. Isn't it? We very well know this formula. You know V2 you have calculated. This VF is this, VG is this. You can calculate X. X is equals to 0.9033. That is correct. I have written 0.9043. 0.46. I think that could also be correct. Okay. Dryness fraction. Okay. Now internal energy, change in internal energy they are asking. Change in internal energy. Next question is change in internal energy. How do you calculate change in internal energy? So very simple. Change in internal energy is U1 is given to you. U1 is given to you in question, right? Look, this is your U1. I'm sorry, there is some problem with the slide when I'm changing. Okay, so this is your U1. This is your initial internal energy. Okay, how do you calculate final internal energy? By using these two. Okay, so initial internal energy is 2638.9 kilojoule per kg. Final internal energy U2 is equals to UF plus X also you know, and UG minus UF. Okay, so everything you know. And what is change in internal energy? Du is equals to U2 minus U1. Can you calculate this for me? I don't want to keep changing the slide here and there. Minus 327. No, I don't think so. I think this option is correct. So it should be around 6 minus 6.434. Okay, let me calculate it because I have not calculated it. Let's calculate it here. Okay. So U2 will be equal to 439.3 plus 0.904 2512 minus 439.3. This is 2313 kilojoule per kg. So U1 minus U2 is equals to 28. Okay, that is 325.8 kilojoule per kg. I think then that is correct. Okay, the change in U2 minus U1, so that is minus. Okay, if I say it is U2 minus U1, okay, so there may be some issue with the question that how it was written, but that is correct. Okay, I need to check from the book that I take it from. Okay, so change in internal energy is this. Now very quickly, can you tell me how to calculate change in heat magnitude of heat transfer? Magnitude in heat transfer. How do you do that? How do you do that? How do you do that? We know the equation. We know the equation. dq is equals to du plus dw. Okay, there is one thing. So Bhavya, what you have done is you have not multiplied it with the mass. That is why you see this is in kilojoules. This is in kilojoules. Okay. Yeah. So now I think you will get the answer. Yeah. Even I missed it, but anyway. So you know dw, you have calculated it. You know du, you just calculated it. So can you very quickly tell me how much is dq? How much is dq? dw you have know, you know, and d you know. This is minus 6 point, how much is it? Minus 6.434. And this was 4.68. So the answer that you will get here is minus 1.75 kilojoule. Okay. Are we on the same page? Minus 1.75 kilojoule. That is correct. That is absolutely correct. So anyway, that was the last question for today. Now tomorrow we will have a quiz session on the app, Byjus Exam Prep app. Okay, and you can follow this link to register yourself. Okay, you can join by this link. Maybe you need registration, maybe you don't. I don't know. I am not sure. Okay, so you can use this link to join that tomorrow's practice session. Okay, and then also you can join me because people were asking for the Telegram channel. This is Mechanical by Vipin Yadav, and that is the link. Okay, you can join through that. Okay, whoever are watching, please join it. So my future classes will be uploaded there. My PPTs I will be uploading there. My schedule I will be uploading there. Okay, so I'll see you tomorrow for this practice session that we have. Okay, for whatever we have covered till now, we will have a session. Okay, not very big questions. Around 20 questions I am planning to keep there. Okay, and I think 1 hour we will keep. Okay, so keep practicing, and I will see you soon with some new classes. Okay, so I'll say goodbye here, and I'll see you soon. Thank you very much.